Gotta center myself in the frame. Which would be like this, I guess. But I don't know, I always sit like this, like leaning on my left hand like this whenever I'm talking. Like always, I don't have anything to say. um, Nothing's really new or exciting in my life, and that's just how it is. Today, Tuesday? Oh yeah. I mean, I didn't really do anything on 4th of July. I just went to sleep. And I slept really good. Uh, like I slept so good. Or no, it was like when I got off work that day, I took a nap, and then I slept so much that when I woke up from my nap, I thought I had like slept 24 hours or something, and I was late for work the next day. But then like that night or whatever, I just slept through all the commotion. There wasn't really a whole lot going on where I live. Like people were letting off fireworks and stuff, but it wasn't really like crazy or anything. And I don't even know if they did like a fireworks show here. Everybody was saying they were gonna do like a drone show or something, but I don't know. That's the problem with working a grocery store job, I guess, is that like you have to, well, at least my schedule or whatever, I don't have a whole lot of time for doing things outside of work, which kind of sucks. I should probably change that. But I would need to find a hobby first. I kind of want to get back into like riding my bicycle, but I need to take it to the shop. So maybe I'll call up. Um, there's like a Trek dealership, or I don't know what you would call it. It's like a they sell Trek bikes and they service them specifically. Um, and they're right here in town, so I need to call them and see like how much is it gonna cost to get my bike fixed again, or at least like in working condition. And there's not much wrong with it, I don't think. It just needs like a tune-up, and it's been sitting, in the garage before before I took it here, and it's been sitting there for a long time. So I'm not sure what would be wrong with it, but probably have a professional look it over. And then, after that, maybe I'll start biking again. And I kind of want to because I gained like 10 pounds since I've been living here. And it's all the sweet tea and all the fast food and that kind of thing. Even though I have a really active job, I eat a lot, I guess. I don't really eat healthy either, but I did buy a watermelon. And I don't know if a watermelon is necessarily healthy, but it's fruit, right? It's in the fruit category. But a watermelon probably has a lot of sugar in it too. But I ate that watermelon in like 2 days. It was really good. I think I might go get another one. And the trick is with the watermelon, you just cut it in half. And if you're the only one that's gonna eat the watermelon, just cut the watermelon in half. And then I took a spoon and you take one half of the watermelon and it's like this kind of. You just eat right out of it like it's like its own bowl. You're just eating like the watermelon out of the rind, which you're using like as a bowl. That's pretty nice. Cutting up a watermelon's not difficult, but it is kind of annoying sometimes. Um, let's jump over here. So, we're doing more BVH stuff today. Um, I think the music is so quiet that y'all can't hear it. Anyway, yeah, more BVH stuff. We're following along with this YouTube video. by Sebastian Legge, I guess you'd call it. Can I open it over here? So we're just following along with this video and kind of coding up little visualizations for different things. And we're not very far into the video. We're about like right here. So this is where you start actually traversing the BVH and finding which triangles the whole idea is behind this is that you want to do a spatial query and find, in our case, we want to know when we cast a ray from the viewpoint of the camera and we cast a ray into the scene, we want to know what that ray is intersecting with. And right now we're only looking at one single mesh. So what we want to determine is what triangle of that mesh does the ray intersect with. And we don't care about multiple intersections, we kind of just care about the first one at the moment. And what we've done so far is we've kind of split up the mesh into different bounding boxes. So everywhere there's a purple square, or sorry, like a purple cube, that's one of the bounding boxes. And this thing is a tree or a graph. So at the root you have this big red box. And then its children are these two boxes, and each of those two yellow boxes, which do have a little bit of overlap. Well, not in this case, because it's like totally symmetric on all sides. Those two boxes will also have two children in the next, like, this is depth 0 at the red box, and then depth 1, and then it just kind of keeps going down. So we've got the structure set up for what we want to do, and now we need to actually query this thing and say, okay, you're intersecting with this triangle. And the whole idea behind this is that if you were to just cast a ray and ask, the mesh, give me a triangle that, this ray is intersecting with, a really naive approach is to iterate through all the triangles and check every single triangle. And that will work, but that's very inefficient. You can imagine you're only going to intersect with, in this case, we don't only care about one triangle, but you're checking every single triangle. And imagine if you had a really complex mesh with like 10,000 triangles or something. Like 99% of your checks are going to return false, but the program doesn't know that. JavaScript doesn't know that. The application doesn't know that, or whatever. It has to check every single triangle. So this is kind of like a way to really like cut down on the number of checks that you're doing. And the way that you do that, really briefly, is that you kind of put sections of the mesh into different boxes, and then you're checking the bounding box. And this is called bounding volume hierarchy. It doesn't have to be a box necessarily, but a box is easy to check, for intersections and stuff. So that, let's go to the case where we have two boxes. So if I shoot a ray where the mouse is at right now, it's only going to intersect that first box. I don't have to check every single triangle yet, because I know that I'm intersecting with the box at least. And then as I go further into there, so now I'm in this side of it. Now I need to check these two boxes. And maybe I intersected with this one, the bottom left one here. And then I recurse again, which of these two boxes? Maybe it's this first one that's closer to the camera. And then here's where it gets weird, because the boxes are a little bit hard to visualize. But you keep narrowing down on this box until you reach some condition where you're like, okay, it's time to check the triangles now. So you can already imagine that's a lot more efficient than checking every single triangle. Now you only have to check maybe like, I don't know how many we have, but is it this? Yeah. So 1, 2, 3, 4, 5. You have to check 5 boxes, and then that's where you end up in like one of these boxes of this size, and then you check the triangles inside that box. And hopefully, you might be able to make some really weird geometry that doesn't, you know, doing this procedure or whatever doesn't really help out with the efficiency. But I haven't really thought about it. But in the general case, right, you should be doing a lot less querying because you're not checking as many triangles. And in like intersection with a bounding box and like array is something that's built into Three.js, but I wasn't really interested in like calculating that and figuring that part of it out. We're just gonna assume that it works, and it works, and we know that it works. That's one thing that we don't have to really like. That's provided by the system, and it's the same thing too. Like intersection with a triangle is supposed to be pretty fast. There's like fast algorithms for doing that. Array with a triangle. But that's also something that's built into Three.js that we really don't have to worry about. We can use like, what do they call it? Functions and methods and stuff that's already provided. So, but today that's where we'll do this part of it, where we're actually going to traverse the BVH or bounding volume hierarchy to hone in on a single triangle. And so this is the ray that they're shooting, and then they found that they intersected with this triangle. And it's also like visualizing the triangles in that box. So it said, okay, you only had to check these red triangles, and these are the boxes that got you there. We're not going to do all that. We're just going to put an outline around the triangle. And I should say too that, we're going to do it in such a way that's not very efficient. We create a lot of these triangles that we could really just use the buffer attribute for a lot of this stuff. I'm not too worried about optimizing things at the moment, but this isn't very like friendly for Three.js development. Maybe in the end we will adapt it to be like built for Three.js, which has a lot of like, I don't know if they would call them quirks or something, but there's a very specific way that Three.js sets things up, and we can probably tailor this file, or this system, if you will. We can kind of tailor it for Three.js, but that's not something that I'm worried about at the moment. So yeah, you can tell there's a lot of stuff, like there's still a lot to go. We're only right here, and that's not even like, I don't know, that might be like a sixth of the way through the video or something. But that's okay, because it gives me something to stream. I don't have to really think about a streaming topic. And I guess when we're all done with this, I'll put it into a playlist and on YouTube or whatever with all the VODs of the stream and call it good. So I guess that's a good introduction. I didn't really draw anything, but I guess we'll just get started. This is a cool video here if you've never seen it. So, we want a way to intersect with, we're going to have an intersect function, and this takes 2 arguments, right? It'll take the node, or I called it BVH node, and then it'll take the ray that we're using. It's going to be assumed that the ray has already been like positioned and oriented and stuff. So we're not going to do any of that. That should happen before you call this function. And we're going to, the way that we're going to test this is that we'll put it in an on move, or like a pointer move event handler. So in that handler, it will adjust the ray's properties, and then we'll check for intersection. And if we intersect, then we will draw, here's our mesh or whatever, and we say that we intersected this triangle. I guess it's purple in our case. Or not purple, sorry, it's orange. So that's a good orange color. Here's the mesh. Here's the triangle that it said this is the one that you're intersecting with. All that we're going to do is just add a white highlight. Like, we're going to color that triangle white, and all the other triangles will still be orange. However this thing is, triangulated, I don't know, something like this. That's a triangle. You know what I mean? This is a wireframe. So that's not very good, but one of these triangles here will have that red highlight. And this one has, here's a triangle here. Maybe it'll be best if we decrease the, what is this, t.ray. That's good enough. If we lower its detail, so maybe like, I don't know what these default to. 32 and 16, so let's do like 5 and 10. That's interesting. Maybe we'll do like 8 and 16. Okay, so now we have like, it's kind of hard to see it, but here's like a slice of this thing. Imagine this is like an orange and you were cutting it, and this is like a slice of your orange or something. These here, there's triangles that make up each of these. Imagine like a box right here, and then it's got a triangle that's, a segment here that splits from top left to top right, and then each of these is split into a triangle. So I guess that's what we'll use for testing. With this intersect function, so this will be another recursive function, because the structure that we have really lends itself, this is a tree structure, right? And those things really like recursive, what do you call it? Like implementations, I guess. You can't do recursion as far as I know. Like, recursion isn't very friendly for GPU stuff, and I think eventually we'll want to move this algorithm to the GPU. But we're going to do it CPU side for now, and we'll do that conversion later on. But it probably would consist of, creating this big array of data, passing that to the GPU, and then probably using some kind of like stack-based implementation for doing the same thing. But I don't know if we'll get there today. That might be for Thursday. Okay, so in the end, this is going to return a triangle. Now, if you did not intersect with it, with the mesh, and this BVH node has, it's assumed that this thing has already been set up. And we have a function for that called create, which takes in the mesh, and it would return you a BVH node that is like, a BVH of this mesh. So the way that you'd probably call this, well, we're going to call it in the on pointer move event. So, it's assumed that your node and your array have already been set up, and then now we're checking for intersection. So this is going to return a triangle, and it's recursive, so we should probably pass along that triangle. This will be null or t.triangle, and we'll just set it equal to null in the beginning, and then we'll return it in the end. But I don't want the user to think that they have to pass in a triangle here, so what we'll do is we'll have like a private version of this thing that almost has the same signature, but oh, it does have the same, well, it'll be like this. And then here we're returning triangle of node and ray, and we're getting rid of this. Or this is not triangle, this is intersect. We can get rid of this and just return that directly, and this is what we'll export. So now when you import this thing, all you have to pass in is your node or your root, where to start from, and then the ray. So the first thing we have to do is check if we intersected the bounding box. So that's easy to do. It's intersects box, and then it's node.bounds. We can check if that is true. Then we need to traverse its children. Or I guess we need to check. I'm looking at my notes on the other screen. We need to check if this is a leaf or not, and the way that you do that is you check if its children are null. So if node.left is null and node.right is null, then this thing is a leaf. And that's where we actually, a leaf in this case is where we want to stop and we want to check the triangles. So this branch here tells us, okay, we've gone all the way down the tree, and now it's time to check the triangles that lie within the current bounds that we're at. And these things are keeping track of the triangles. There's a lot of duplication, which we will fix in the future, but right now it's just got duplicated data. The root has all the triangles, and the children just have subsets of the triangle array and stuff. There's actually a really nice way to cut down on the duplication by just using indices into a global, not global, but maybe some triangle list or whatever, and you're just kind of keeping track of the indices. And the indices of that list would be okay, I have the triangles that correspond to, 1, 2, and 3. And then some other box says, well, I have the ones that correspond to, 4, 5, and 6, or something like that. And, the root will actually have all the triangles, but each of these, smaller boxes only has a subset of that. And it doesn't have to keep a list of it, it can just refer to the root list by keeping track of the indices that it cares about. I think that makes sense, but we're not there yet. So let's just keep going. So if it's not a leaf node, then we need to recurse, and we need to keep going down, checking for intersection with the box. So here, it's kind of interesting. If you check node.left, it doesn't know that it's not null here. And the reason is that in this branch here, you don't know which of these sides of the if statement were true or not at runtime, I guess. So, if I jump here, then one of these was false, but I don't know which one at runtime. Right? All I know is that I jumped into here. And there's two ways I can do that. Either this one was false or this one was false. But I don't know which one. So I can't just do like and then we're returning that triangle, so it would be like this. Node dot left, and then array, and then triangle. Can't do this because it still thinks that left could be null. And it could be if, you know, this, let's say left was a triangle, but right was null. Or let's see. What I'm trying to say is that you have to kind of put this in an if statement as well. So if node.left is not null, then we'll do this. And then we need to do the same thing for the right side. I think this is, yeah, intersects box. This will return a boolean, the other will return the point of intersection. Oops. Yeah, so that's the recursion part. Now we need to actually run through these triangles and return one of them. You know, we know that we intersected the box, so we should, well, maybe not. Actually, if you had a case like this, that is such a bad drawing. If you had your box like this, but your triangles inside of it were just a little part of the box here, and you casted your array like this, you're gonna miss the triangles. You intersected the box, but you missed triangles inside that box, so you still could return null. But we still have to check the triangles anyway. So for t of let's see, t of node.triangles, that's where we're looping over all the triangles. We're going to say intersection equals array.intersect triangle. And then you can tell that like the triangle class here is not really for intersecting and like drawing and stuff. It's more like a class for doing like trig and math on triangles and stuff, because otherwise this thing would take in a triangle, but it doesn't. However, we could just pass in the properties of the triangle one by one. You can tell that this isn't very efficient. There's better ways to do this in Three.js, but we'll just roll with it for now, and it'll be good enough for what we're doing at the moment. And then we later on, when everything is working and we're all satisfied with it, then we can come in and you know, change how these things are stored and how they're passed around and stuff. This backface culling, I haven't really figured out what this thing is, but I'm gonna set it to true, and that's just because when I was testing this thing out, I had better results when I set this thing to true. So I'm just gonna set it to true and not really think too much about it. The target is where we're gonna actually put the result. So we can create a target new t.vector3, you know, outside the loop, and we'll put it into target. This thing could return null, meaning there is no intersection. So if it's not null, that's where we need to update the triangle right here. So if intersection is not null, that means that we had an intersection. We need to check the distance from that triangle's, or actually it's from the intersection, because the intersection is just a point. And the way that we're going to test with this, you know, maybe we intersected a bunch of triangles, but we only need to pick one. And we can't just like break out of this loop because we want to return the triangle that's the closest. So we can't break on the first intersection because we might have intersected first with something that's you know, here's the box, let's say, and then there was a triangle up here, a triangle back here, and we cast an array like this. But the first triangle that we checked was this one. And we can't break and return this one because there's something that is closer. You know, here's where the camera is or whatever, and we cast an array from the camera. So we have to check every triangle, but we're going to keep like the one that is the closest. And that means that we need to pass a bit of state every time that we call this underscore intersect function. We need to pass along like the best score, if you will, for the current triangle. And since we're talking about distance, let's see. Yeah, we want to return like the minimum distance. So if there was an intersection, we need to check the distance from the point of intersection to the ray's origin. And you can do that like this. You can do intersection dot, or sorry, it's intersection distance. You would do, yeah, intersection is a, dang, I cannot spell today. Intersection is a vector 3, and it has this distance squared, or distance 2 squared, and it would be ray.origin. So how far away is it from the ray? That's the intersection distance. If that is less than the like distance squared or whatever metric we're using here, and it makes sense to use the distance, then that's where we'll actually say, okay, this triangle is closer. We need to set this triangle equal to the current triangle, whatever triangle we're at in this loop. So if the intersection distance is less than the distance squared, then the distance squared, maybe I should call this, we'll call it intersection distance. But I do want to kind of tell you, like, you know, as you call this function, it's not just the distance, it's the distance squared. And the reason that we're doing that is because we don't care the actual value of this thing. All we care about is that it's less than this one here. So to avoid doing like a costly square root function or a function call and all that, you can just compare the squared distance, because a less than b, that's also true if you square these things. You know, squaring is, I guess they call it like a linear function or whatever. So if you square both sides, this is still true for all inputs, positive or negative, right? If this was true, then this will also be true. So distance squared is equal to the intersection distance, and then the triangle is equal to t. T is the name of the loop, like whatever current triangle we're looking at. Oh. Okay. Oh, this needs to be t. Yeah. T, and then what's the problem here? Distance squared. Like that, and then yeah, we need to pass along the distance squared. So it starts out at infinity because you know, if we did find a triangle here, there's never like, it should always be less than infinity. Whatever triangle it is, if we found one, its distance will be like finite, right? And any like number that you compare with infinity, you know, let's say a is some number, It doesn't matter what this number is. This thing's always going to be true. Yeah, so now what? That's kind of all there is to it. But now I need to actually check that this thing works. So over there in the demo, the way that we can check this is when I move the mouse around, I just want to cast a ray from the mouse position into the scene and then check for intersection with the mesh or with the bounding box. The bounding volume hierarchy, which or the BVH. That's the easy way to say it. So in Svelte you can do on pointer move, and if you just like console.log hello, you know, every time I move the mouse, every time there's a move event, it's logging out hello right here. So we actually want to get the event, and this is the type of the event. And the current target is an HTML element, which is nice. It'll be whatever, like, it'll have the same type as this thing here. And one of the properties of this thing is the offset and the Y offset, X and Y offset. And that will tell you, in pixels I think it is, how far you are from the top left corner of the element. What we're going to do is make use of this thing called set from camera. We'll do const raycaster is a new raycaster. And here's where it becomes like really painfully obvious that this is not the intended way to do like ray intersection tests, is that there's an intersect object function on this thing. And this calls into like if we had a object 3D, and this actually has, yeah, this raycast method on it, which you can overwrite. And meshes have their own raycast method, but you can actually overwrite this thing if you were to like inherit, you know, I don't know what to call this, M extends mesh. You could overwrite that raycast. I don't think you have to pass anything there, but you could say raycast. I think you might have to call super. Yeah, like this thing is intended to be, yeah, it's abstract right here. Oops. So eventually what we'll probably do is extend from mesh. This may happen like way down the line. Is that we'll actually convert what's in this file to some kind of class that extends from mesh, and that way we can call what did I get rid of? I don't know, I think we're okay. Anyway, and then like you can just, you know, pass in the whatever like we create, that class that I just talked about. You can just pass in the class here, like our BVH mesh or something right here. But we're not there yet. So we're gonna go the long way, and I think it's a good, important thing because it kind of demonstrates how this is all kind of engineered under the hood, I guess. Like how it's kind of what's happening behind the scenes, I guess. So, we have a raycaster, and jumping back here, raycaster has this set from camera function. And it takes in the coordinates, which are going to be in the range from -1 to 1 in both the X and the Y, and then the entire camera. So we don't have this chords yet. I need to make a variable to hold that. New t.vector2. But the way that you convert a mouse position like this into that -1 to 1 range, you need to do it both in the X and the Y. So you would take this is like, you know, we've done this plenty of times. Let's say that the canvas goes from 0 to 800 or something. It doesn't really matter what this thing is. We could even call it A or whatever. The offset will tell us a number between this range, offset X and offset Y. And then what we need to do is divide out by the maximum, and that will normalize it so it goes from 0 to 1. And then we need to shift it in such a way, or maybe scale it up, shift it around that range so that we get from -1 to 1. So you would take some, you know, this is the offset value. Take your offset, you divide it by A, and that will go from 0 to 1. But we want it to go from -1 to 1, so you multiply this by 2, and it'll go from 0 to 2, and then you subtract 1, and now you're in that range, -1 to 1. But it's a little bit different for the Y, and that's because of the way that like the positive Y, I believe, is in the, I don't know, it's flipped. We need to flip the Y around. So the X, that's easy enough. That's offset.x, or sorry, offset X divided by event.currentTarget.width, or it's the client width. So that's 0 to 1. Pick that. And then we subtracted 1. Or no, we multiplied it by 2. And then we subtracted 1. So that's this step here. Let's call this normalized device coordinates X. And then this will be kind of the same thing, but we need to flip the 1 and -1. So this is what it ends up being. So kind of to follow along with this, we know that this guy is in the range 0 to 1, and this should be Y in height. So when you multiply it by -2, now you're going from 0 to -2, and then when you add 1, now you're going from +1 to -1. And that's because in Three.js, the Y dimension is opposite of whatever, like, you know, positive Y in canvas space, or can I call it that? In the HTML world is the opposite of what it is in the Three.js world. In Three.js, like, positive Y is up. So yeah, that's true. So yeah, if I draw that, so in Three.js, this is positive Y, and then in your normal like canvas or like HTML, you know, 0, 0 is up here, and then positive Y goes down. You know, like here's your canvas or whatever. So we just have to flip that around. Then once you have the indices, you can do chords.set. Is it set? Yeah. Indice X, indice Y. And then we can actually move this because it'll return that vector. You move it in there. I don't think the format is working. Oh, it is. Okay. So now the Raycaster's ray has been set properly. And like I mentioned, you would probably, in the end, you would want to call Raycaster.intersect object. But we're actually going to use, like, that's what I want to do in the end. And that way, you know, you can use this anywhere you can use Raycaster. And it'll be a very nice API to use and all that. But today we're just going to use the ray directly. So we need to do, yeah. This intersect function is coming from BVH. We pass in the root. We called it the root up there. And then the ray, caster.ray. So that looks good. It says, yep, a triangle or null if you did not intersect anything. And then we can check, oops. If triangle is null, we don't really want to do anything. Just return. But to kind of help out with TypeScript a little bit, I'm going to put this into a variable. We'll call that intersected triangle, which I don't like the name of, but it kind of tells you exactly, or let's call it like intersects triangle. Kind of implies Boolean. Intersected triangle kind of sounds like you're returning a triangle, or, right? It's the name of a triangle. So if there is no intersection, then we'll just jump out immediately. Otherwise, we need a way to visualize this thing. Yeah. So I was thinking about ways to do this, and the reason that I don't want to do like a normal mesh is, like it could be possible, it would be possible, right, to move a certain mesh to that location, the location of whatever triangle we intersected with, and then set the vertices such that, you know, we're only going to draw a triangle, it's only got 3 points, and to adjust the vertices to match with whatever triangle is here. But that involves like sending data to the GPU every time you intersect, like updating the buffer attribute and all that. Which isn't too bad for like just 3 points, but it didn't feel right to do it that way. So I'm actually going to use a line geometry, and I got this idea from one of the Three.js examples. And let's see if I can find it. Maybe this one. Yeah, this is the one. So there's a white outline between whatever like triangle the pointer is currently over. And the way that this thing works is that it uses a line geometry. And then when it intersects, right here, it just updates the geometry attribute directly. And I suppose that calls needs update, or sets needs update to true. Or I don't know if it does or not, but um, we just want a way to kind of like highlight whatever triangle is the intersected triangle. So this avoids updating a mesh like position buffer or a buffer attribute and calling and setting needs update to true and all this other stuff. So I figured we could do it this way as well. This is still pretty fast, even though there's so many triangles in here. And it's just using the like built-in, like this is just a normal geometry and all that. Yeah, just a normal mesh, I would assume. Which brings up a good point that, you know, this current way that we're doing things is based on the geometry. It doesn't take into effect any kind of like rotations or scaling or anything like that. But at the end of this video, there's a section on transformations. So if the like mesh is rotated or something, or if it's scaled by any way, yeah, and supporting multiple models and stuff. So hopefully he covers, you know, it's been like, I think I watched this video when it first came out, but I don't remember what is in the what's in these parts, you know. So hopefully when we get there, like we can make a system or whatever that handles any kind of rotation and any kind of transformations. I'm really only, I mean, the part that really interests me is like, how do we do this on the GPU? But got a ways to go. So over here, what we can do, we don't have a geometry yet, and we'll need one. So what we'll need, let's do this outside the like the HTML part of this. I'll do const line equals new line. There's a weird way to do this with well, actually, I think we're okay. I was gonna say there's like interesting way to do this with the web GPU side of things, because Three.js has two kind of like libraries. There's the web GPU stuff, and then there is the WebGL stuff. And I don't necessarily think that all of the add-ons have been converted to web GPU, but I think we're okay. I think we can just use stuff from the like core library and we'll be fine. So this needs a line geometry and material, but we'll just use the default material. Oops. So that's a new buffer geometry. And we'll do line geometry dot set attribute. We need to set the position attribute. The second argument here is the attribute, so let's call it line position attribute. And let's make that outside as well. That'll be a new t.buffer attribute. What you pass in here is a typed array. We're going to use a float32. I think that makes sense. So we'll do new float32 array. Like if you've never set up your own buffer geometries yourself, this is pretty easy. Pretty easy stuff. That's like if you look at the source code of like the sphere geometry or any of the geometry primitives, it's doing stuff like this. and then it's like pushing points into an array based on some kind of function that generates those points. But an argument here, because these things are kind of like, you can modify things inside them, but they can only ever contain numbers. If you've ever worked with typed arrays, they can only ever contain numbers, and you can modify like different positions in the array, but you cannot push and pop things from the array. So it's got a fixed size. And that's because, you know, a normal array in JavaScript or whatever, you can push any kind of data you want into the array. And it's dynamic as well, in that you can slice anywhere you want and modify everything you want about the array. But these like typed arrays are much more restricted, and the reason is that it's much faster to loop over a typed array, that you know the size of everything in the array. It's going to be a float 32, and you know that like the offsets or whatever are fixed, right? So there is like no additional logic needed for well, I guess I don't know. I don't know if that's necessarily correct, because if you're storing pointers into an array, I don't know how these things are coded under the, like, you know, at the engine level and stuff. But I bet that a JavaScript array is just a bunch of pointers in the array. So iterating over an array in JavaScript is probably like, I wouldn't say it's fast, because those pointers could live anywhere, you know, and you might have to reach out to the cache every single time that you iterate or whatever, because you know they're not contiguous in memory. I'm pretty sure these typed arrays are contiguous in memory, so you get a lot of cache hits and stuff. You don't have to access memory as often, all that kind of stuff, all that low level stuff. That was kind of a detour, but there's going to be 3 points in this array. And each point has X, Y, and Z. But we need 4 points, because these are going to be like line segments. If we draw this out, let's say our triangle is like this. We have an A, B, and C. And each of these has an X, Y, Z. So we're going to push A into the array. We're going to push B into the array. Not actually going to push. We're actually just going to modify, you know, values that are like positions in the array. So, you know, we're just going to like say, okay, we want to change whatever's here to one of these, and change whatever's here to whatever, you know. We're not pushing, we're not popping, we're just kind of modifying data that's already there. And I don't know if I would like calling it modify, but we're setting, you know, let's say this is 0. We're setting that number to, for instance, like b of x or something, right? So to get the first segment, so this has 3 segments, right? It'll be AB. The second segment is BC, like this. Oops. And then the third segment is actually CA. So if you, the way that this line works is that it takes every 2 of these and then makes a line between them. So if you collapse this, like you get rid of the duplicates, we're going to draw a line from A to B, and then B to C, and then C to A. But, you know, these two are the same, so we can just cut this into 1, and then these 2 are the same, and we can cut that into 1 too. So what we're left with is A, B, C, A. There was a geometry that would, oops. This thing here is the same as line, which we're currently using, but it would connect the last vertex to the first vertex. But if you use this thing, okay, it's not, I don't think it's deprecated, but at runtime it'll say like, don't use t.line loop, use t.line instead. And then all that really means is that we have to push in the last, I keep saying push, but we have to set the first and last vertex to be the same thing. So that's why this is 4 elements in here instead of just 3, because we're going to put A, B, C, and then A again. That way we don't have to like jump back to the front to grab it and put it in the back and so on. And then the last thing we need to do is add the line to the scene. But down here where we know that we're intersecting, we need to do line dot set from points. I guess it's line geometry dot set from points. And then we'll do triangle dot A, triangle dot B, triangle dot C, and then lastly triangle dot A. And this needs to be an array. Oh, I think these could be null. So let me see. If we do it like this, I'm pretty sure what we need to do is tell TypeScript that this is not null. Oh yeah, so we need to do that. Now I think it should work. Let's see. Yeah, so should probably put something in here to hide the bounding box. But as I, move around this thing and I'm intersecting with the mesh or whatever, it's, changing the position of these things, right? It's setting the line geometry based on the triangle that we get out. So that's working. That's nice. Let's see how it handles like a sphere with more detail. So if we do just the default, yep. Let me get rid of this. You can see too that, it's only getting the first triangle. That makes sense. We're only ever like dealing with the first triangle. But we intersect, like if I put the mouse here, we actually intersect 2 triangles. The one in the front, and then this one, the smaller one that is like right here. But we're only ever returning the closest triangle. And that'll be another thing that we have to be aware of when we do this raycaster stuff, is that you may want to only return the first triangle. You may also want to return all triangles that you intersect. If you had a geometry that looked like this, for example, and you cast an array like this, you'd intersect probably like 6 triangles. One here, here, and here, and here, and here. So you may want to return all 6 of those things. But, for testing and where we're at right now, we'll only probably ever use convex geometries, convex geometries, which means that there is no point, convex geometry, I've explained it before, but any 2 points inside of this thing, the line between them will always be inside of the blob here. A convex geometry is one where you can take 2 points, and the line between them, part of that line lives outside the geometry. But I'm pretty sure that in the concave, I'm sorry, this is concave. This one is concave, and then the other one is convex. The way that I remember that is that, like, there's like a cave right here, right? And then this one is convex. But what I'm thinking is that in the convex case, you shoot any ray, if you intersect with the mesh, the convex geometry, you'll only have 2 points that you intersect with, where you entered the geometry and where you exited the geometry. I can't think of a shape that would give you more than one intersection, or more than two, I should say. Because as you enter the geometry, you're going to have to exit. And the only way is that, the only way you would exit is if you were leaving the geometry. And then, you know, you're leaving here. In the convex case, this doesn't happen. Like, this would only always ever be covered. And the only time you're leaving it is if you're leaving the hole. So that's not a very rigorous proof, but I think it makes sense. Then there's one little optimization that I want to make with this, is that, you know, we're running this code for every mouse move event, and we should, but if we get the same triangle out, you know, like right here, we're getting the same triangle out, we don't have to do this set anymore. We could test whatever triangle that we get out with the last triangle. If they're the same, then we can just return early. There's no updating that we need to do. So up here we can say last triangle equals null, and the reason for that is that we don't intersect with anything in the beginning. This should actually be triangle or null. And then here we could say, you know, if last triangle does not equal, well, let's do it like this. If triangle equals last triangle, then we'll just return. Otherwise, we can do last triangle equals that triangle. Probably want to do that at the end. You can actually return all the way like right here. So this is where we get the triangle out. That's the first thing we do, is check if it's the same triangle or null. If it's different. If it's the same, then we don't need to do anything. If it's different, that's where we need to do all this. So that should still work, and then to kind of demonstrate that this was a little optimization, we can do the only time that this will get printed is if we change triangles. So here I'm moving the mouse and I'm in the same triangle, but as soon as I leave, it will run again. So I'm trying to think. That was really quick. I didn't think we'd get done that quickly. Um, I'm gonna see what this would look like if we hide the mesh. So right here, we'll do. That's interesting. I guess, you know, what we can do for now. So I don't have. I mean, the next step is to set this thing up so that it's GPU friendly. And I'll talk about what that means next stream on Thursday. Um, but really briefly, what that means is that we can't have recursive calls and all this like duplicated triangle stuff we need to get rid of. So we'll just have one giant triangle list, and we convert these triangle property. Where is it? Like we'll just have one big triangle list, and then each of these BVH nodes, left and the right, will like they'll still be there, I guess, but they won't have their own triangle list. They will just have a list of indices that refer to the triangle list. And the second part of that is that the triangles need to be sorted so that where is it? So like at the moment the triangles are just all kind of scattered around. And I don't know if that's true or not for these geometry primitives, but what we need to do is make sure that all the triangles, like let's say that this is our bounding box. That's not very good. Let me redraw that. Here's our mesh, and then we've got two boxes, and then, you know, this mesh is comprised of points or triangles, right? It's got a bunch of triangles. I'm not going to draw them all, but, you know, all these triangles on this side and on this side. Those could be out of order. What that means is that we want all the triangles that live on the left side to be kind of like on one side of the array. And then we want all the triangles that live on the right side to be on the other side. And then for that left side, we're going to split that as well too. So that, you know, if we split it like this is now, you know, all the triangles that live in LL are on the left side of that sublist, and all the triangles that live in LR are on the right side. So there's a lot of like shifting the data around, shifting the triangles around so that they're in order. And he shows the code to do that. Here, I think. If I can get rid of the captioning, yeah, right here. So there's a lot of like swapping the triangle data around. And that'll be what we do next stream, is getting this to be more GPU friendly, and then you know, converting the recursion to I don't know what that last word is, but we got to get rid of this recursive calls and stuff because we can't do recursion on the GPU. I mean, I think you can. I've never actually tried it, but if you try to do Like if I had let's say this takes in a float. Um, let's see if this works. Oh, I need to put it above. Oh yeah, this has to be 0.0. Why did they do the errors that way? That's awful. Wrong operand type. Yeah, I know. This needs to be 0.0. Recursion function call in the following call chain. Yeah, I guess you can't do recursion. And it's cool that it knows, like, there's an error for that. Specifically, recursive function error. Let's see what the clankers have to say. That makes sense. Yeah. So we'll probably use some kind of stack-based solution in a for loop and stuff like that. Well, that I learned something today. Yeah. What were we doing? Oh, I need to get rid of that. Let me do that real quick before I forget. Oh, that's not it. I was always wondering why that video opened up at a certain time. It's because that link has a timestamp on it. Okay, so I guess the last thing I want to do today at least is a little bit more controls. So I want you to be able to hide the bounding boxes. So where we have the groups, these groups are just inside of an array. So we'll do like oh yeah, I have this set so that we're this is kind of weird, but as we increase the depth here, we're setting like the visibility of something in the array. We're just toggling it. So I could put all those groups into a parent group. We do like this, like BBH groups equals a new group. BBH groups Yeah. Do that. We need to add it to the scene. We do scene.add. And then down here, where does this get set up? Yeah. Yeah, so this is an object array, but it's expecting a group array, so we can change that. It's a little bit more generic. Let's do BVH group. Oh, actually, do we have to do this? Oops. Yeah, we can do, well, let me think. I want to do that, and then let's leave that alone. What I'm gonna do is, dang it. We're gonna do that. We're gonna do this. Yeah, for every group, we'll add it as a child here. It's a little bit of duplicated data because we already have an array, so I might clean this up later on. But yeah, children is just an object array. So we could actually come down here. Where is it? Do BVH groups children. Let's see if that still works. And we want a button that toggles the visibility of like the BVH group altogether. Add binding BVH group visible show BVH. Yeah, that's what I want, so that it's a little bit easier to see the triangle. Now let me think if I can fix this. Oops, I keep doing that. Do I want to return a group there? I guess. Oh, I mean, I kind of like that. This returns an array, but maybe we should return a group. I kind of stopped explaining what I was doing there for a moment. Uh, yeah, this will be a new group. So let's see, we'll do groups that children at depth. If that's not true, then we'll do groups dot add. Oh yeah, but this returns the parent. There's no at return on this. I don't like that. What I want to do is say, you know, if there's already a group there, then just add the box to that existing group. If not, then we need to create the group. This won't work because this returns groups. Well, let me keep that so I don't forget it. I've never known why there was a separate function for adding objects. But let me see. Oh, I already have it right here. Oops. Let's go to the source code all the way down here. And then we want to find add. Add object. Okay, so you can add more than one object. Oh yeah, you need to maintain the like parent and child double pointer thing. So that's weird, but makes sense. Yeah, that's interesting. I didn't know that there was an error for this. Oh, and it dispatches an event. Yeah, so there's a little bit more going on here than just setting properties and stuff. Okay, so if a group already exists, dot add, we'll add the box. That could be undefined, so if group is undefined, then what we'll do is we'll do groups.add new t.group dot add the box. And we can even take this further and say like this. So let's read this. If we have an object at that depth, what do we do if we do like groups.get? We have by property, by name. That's probably doing a traversal as well. Well, yeah, let's read it back. So we find, we look at the children. If there is already a group at that depth, then we'll just add the box to it. If there is already a group at that depth, that will also return the group. But if there's not, we check that here. If there's not, then we need to add a new group that has that box. And we add that. Yeah. Okay. I think that's right. Oh, but now we don't see the... Yeah, this isn't right. Oh yeah, and this was, I think this was setting the visibility to false more than once. Because if it's already there, it should already have its visibility to false, set to false. So anytime we create a new one, then that's where we need to do this. And we'll do groups.add group. I don't like the way this is worded. I don't like this. Let's just do that. Okay, so there. If parent is undefined, that means we need to take the groups and we'll do a new group. And we'll add that, and then we'll also set its visibility to false. Otherwise, we'll take a look at parent here. Parent.add box. But why is it invisible still? Oh, wait a second. Wait a second. Got an error up here. Any more errors? No. That's void. So let's see. Yeah, and then here we need to return the group. Groups. Why is it undefined though? Oh, we return groups. Both cases? Oh no, something broke for sure. Well, I will figure that out off stream. Go back to the beginning. All the way back to here. Oops. Yeah. But this like setting, if it's false or whatever, if there was already a group there, it should have its visibility already set to false, and we don't have to do this. Anytime we make a new group, that's where we do have to do that. So we'll do create group. Yeah, I guess that's a little bit simpler. No, that's not right. Oh no. What in the world? Yeah, I need to play around with this on my own time. Oh yeah, that's outside. Okay, okay, okay. Let me get this working and then I think I'll be done for now. New t.group, group.visible is false. And then we do okay, does that work? Yeah. Yeah, it's oops. So that makes sense. But I do want to fix it so that we don't have to do this like double array thing where we got a group array out here and then we just, you know, move all the data over to this BVH group. We could probably do that in here. Well, we could definitely could. And then yeah, this still works. Need to move the camera back a little bit more. How did I do that? Did I do that? Are we translating the camera at all? Yeah, right here. Okay, so I'll do, like always, there's some work to do off stream. I try not to do too much work on this off stream. Just try to get things to a point where like, okay, everything's working. Like reach a good stopping point or a good like mile marker or what's the term, like milestone or whatever, right? And then we continue on. Um, so next stream, I'll go over that again real quickly. We'll do the triangle sorting. We'll do the triangle, like big triangle list. And we'll do the triangle indices for each node. I don't know if we'll get into this part of it, but next stream will be Thursday, probably around the same time. So that's where we'll see each other again. Yeah. I'll have a good day. So awkward. That's okay though. Okay, I'm going now if I can find my scene. Where the heck is the scene? I don't know why I put it in here. Okay, everybody, I hope you have a good day, and I will see you next time on Thursday. Bye.